In this example, we analyze differential equation of first order using a differentiator and so on. So in this example, consider simple differential equation. The first order derivative of y of t plus c of y t is equal to this one, this x of t for all t and c to be some constant. And we want to analyze. Assume that x of t is a white noise with autocorrelation function, this one, if you want to analyze it. So we could easily find the transfer function of this differential equation, because if you, for a deterministic signal, if you take, obviously remember that Fourier transform doesn't exist for this stochastic process, but if they were deterministic, you would get j omega y of omega and then plus c y of omega equal to x of omega. And then from here you could say that y of omega divided by x of omega is equal to 1 divided by c plus j omega, and this is equal to h of omega, which is Fourier transform of this LTI filter. So from here, you could say that power spectral density of the output is equal to the power spectral density of the input times, so this shall be equal to sxx of omega times h of omega to the power of 2, which is given here. Remember that the Fourier transform of autocorrelation function, Fourier transform of delta is 1, Fourier transform of 1 times this is going to be. So the power spectral density is flat, is constant, because this is white noise. And the power spectral density of output is power spectral density of input times power gain of the LTI filter. And obviously, this guy is equal to this one. So if you put and here this guy is equal to Q. And then magnitude, this, assuming that C is a real number, this is going to be C to the power 2 plus omega to the power 2. So if you calculate it, you get this function. So the power spectral density of the input is constant. At all frequencies you have equal energy, S x of omega. And h of j omega is a function like that, which is here you get 1, and then at high frequencies this filter decays, so it has a bandwidth which is controlled by C. So at frequency 0 you get 1 over C2, and then at omega equal to C you get 1 over 2. So the 3 dB means that your gain is divided by 2. So these locations, so the bandwidth, the 3 dB bandwidth, BW, let's say 3 dB, we denote it like that, is equal to C. So this is the frequency that your gain is half of the maximum gain. And then output power spectrum is equal to this one. So you can calculate. So remember that at omega equals C, here you get 1 over a square root of 2C. So, but this is not power gain, this is power spectra. Power gain means you put 2 here, so you don't have this square root here. So the power spectral gain of the filter is the gain that is multiplied by the input power spectrum to produce the output power spectrum.